Today is section 5.4, day 3, and we're still looking at the fundamental theorem of calculus, and we're going to use that fundamental theorem, particularly part 2, to calculate the area between a function and the axis, the x-axis, analytically, which means calculating it by hand. And so the fundamental theorem of calculus part 2 is going to come into play as we need to evaluate that definite integral by hand. And this is a very typical process to have as an AP question on both the multiple choice and the free response no calculator. Here is really a kind of a summary of the process of how to find the total area analytically. So in this case, we have this quadratic here on the domain from 0 to 3. And so what we want to do is, if we want to find the total area, which means treating all regions as positive values, then it's really important for us to know whether or not this function, 4 minus x squared, crosses the x-axis and goes into this negative region at all in this domain from 0 to 3. So the first thing we want to do is partition or separate the function and so that we can allocate areas as positive or negative. So that involves finding the zeros and finding where it crosses, right, which is where the function value is 0. So finding the zeros it's an algebra 2 skill. We take the function, we set it equal to 0, and we solve this. So we see that when we solve this, we get an x value of plus or minus 2. So we know that this quadratic, this upside down parabola, crosses right here at 2, also at negative 2, but since that's not in the domain, that's off to the left of the viewing area here, we're not going to worry about negative 2. So we know the function crosses here at 2. And then we have to separate those into subintervals so that we can find the value of each definite integral. So in order to do that, we need to graph this. And a lot of times you won't have a graph given to you. You'll have to make it, just kind of sketch it out. So the easiest way to sketch that out is to just plug in each domain value, 0, 1, 2, and 3. Plug them into here and plot the points. So and here are the points here. So when x equals 0, 4 minus 0 is 4. So there's the first point. When x is 1, we get 4 minus 1, which is 3. When x is 2, we get 0. That's our 0. And when x is 3, we get 4 minus 9, which is negative 5. So the parabola in that part of the domain looks like that. So here's the first partition. The first partition is above the axis, so we know we're going to have a positive integral if we go from 0 to 2, when we're also going to call that a positive area. So in that case, the integral and the area mean the same thing. And then this region here is negative. So we're going to have to integrate that portion from 2 to 3 and get its value. And we're going to have to add the absolute value of those two things. So for step 2, we're going to look at that green subinterval. And so we're going to integrate from 0 to 2. And we're going to integrate the function 4 minus x squared dx. So we're going to go ahead and, like I said, this is by hand. This is analytically. That means by hand. So we're going to go ahead and reverse our derivative rules. So the 4 becomes a 4x. And x squared becomes, we bump up that power to 3, and we divide by that new power 3. And we're going to evaluate that at 0 and at 2. So plugging in 2, we get 4 times 2 minus 2 cubed over 3. And then plugging in 0, we get 4 times 0 minus 0 cubed over 3. So we notice that that entire right hand, the lower limit value is 0. So we can ignore that since all that makes 0. Evaluating this gives us 8 minus 8/3. And so we're dealing with fractions again. And so I'm going to think of 8 not as 8 over 1, but I'm going to think of 8 as 24 over 3. So I just multiplied 8 by 3 to get 24. And if we think of this as over 1, then 1 times 3 is 3. And so now 24 minus 8 is 16. So the value of this definite integral is 16/3. And that's also the value of the area. So continuing with step 2, now we have to do the red subinterval. So the red subinterval, when we do the integration, we're going to get a negative value because it's beneath the y-axis. So now we're integrating from 0 to, or excuse me, not from 0, from 2 to 3. We're still integrating the same function. That's this function. So the region between this function and the x-axis is this region here, not this region. And so we go from 4 to, the function is 4 minus x squared dx. And if you notice, we're integrating the same function. So we've already integrated it before. We get this. And so now we're going to just, so the new part is plugging in the upper bound 3. So we have 4 times 3 minus 3 cubed divided by 3 minus, and then we're plugging in 2. And we've plugged in 2 already when we evaluated the green subinterval. So we know this value. We can go back to the previous screen and find this value because the value at 2 was the value of this region here. So that's actually 16/3. So let's go ahead and evaluate this. This gives us 12 minus 27 over 3, which is 9. So no fractions there. Minus 16/3. We know this value ends up being 16/3. So we end up with 3 minus 16/3. I'm going to think of 3 instead of 3 over 1. I'm going to think of that as 9 over 3. So 9 minus 16 is negative 7/3. So this red region is negative because it's beneath the y-axis, and that's negative 7/3. So while the value of the integral is negative, since we're being asked to find the area, we're going to treat that as a positive value because area is a positive value. It's a geometric space, so to speak. So step 3 then is we're going to add the absolute value of these values. So we have the total area then being 16/3 plus the absolute value of 7/3, which means we're just saying 16 plus 7, which is 23/3, which is basically 7 2/3. So that's how to find the area analytically, in other words, by hand. Now we're going to look at how to find the area numerically, and you've done this before. This involves fint. I'm also going to show another way to do this too, though. So here is, again, the values of the integrals. Notice it's negative, that's why I'm saying the value of the integrals. So to find the area numerically, though, it involves using your absolute value function on your calculator. So if we want to, and this is actually really slick because we can do this all in one step. We can go ahead and take our function and integrate it over the entire domain from A to B, as long as we use the absolute value signs. So I can start at 0 and go all the way out to 3. I don't have to split it up as long as my absolute value signs are here, because making this number positive is doing just that. It's taking the absolute value of the function and flipping it upward like this. So that's what taking the absolute value of the function is doing, and your calculator can do that for you automatically. So for our problem in particular, we're going to use our math 9 key. That's our fn_int key. And we're going to go ahead and go from 0 straight to 3. We're not going to split it up. We're going to use our absolute value functions. And so these absolute value bars you can find under math, number, and you see ABS. It's the first option. And when you do that, you get this answer, which is a little different than the real analytic answer. Remember, the real analytic answer is 23 over 3, which is 7 2/3. So you have to acknowledge the fact that this process on your calculator is actually doing a Riemann sum, and so it's getting close, but it's not exact. So you have to recognize that when you get 7.666666, and then you get something a little fishy down here at the end, that's really 7 2/3. So that's kind of what you have to really recognize, that the analytical answer there, 23/3, that you have to recognize this as 7 2/3. So when you have to give an exact answer, you should be relying on this form of the answer, not your calculator form. Now there is another way to find this value on your graphing calculator, which is kind of neat. You can use your grapher. So if you don't have your graphing calculator, pause the video right now and get that out. And we're going to use the y1 or the y equals function. And so what I've done here is I've embedded a video. So in Y1, I'm going to graph the absolute value. So there's that math number, absolute value. And I'm going to go ahead and put in 4 minus x squared. So there's my function, and then I'm going to graph it. Now I'm going to set up the window so that I'm in the domain. So my domain is 0 to 3. I graphed from -2 to 5. I don't need the fourth quadrant, so I started at -1. I'm going to go out to 6. And I'm going to go ahead and graph this. And so there's the absolute value, just like it's showing on the screen. And so we need this region and this region. And we can accomplish that by doing second calc. And down here at the bottom is an integration function. And so my lower limit is going to be my 0. Okay. My x equals 0. That's my lower limit. My upper limit is going to be my x equals 3. So x equals 3, and then it's going to color in everything from 0 to 3. And here's my answer. So again, it approximates it like the graphing function did. We have to recognize that as 2/3. So just kind of to recap, in Y1, you use your absolute value function to get the graph there, the absolute value of the graph. And you use your second calc key, and you pick option 7. And that colors, and I think this is a great reinforcer about area being positive, is when you graph this, you have everything in the first quadrant, or everything at least up in the positive y, and there's that approximation we got earlier. So at this point, you should be able to do the day 3 homework, or if you want to do the proficiency quiz to cover all 3 days instead, that's fine. So that kind of wraps up finding area specifically analytically and using your graphing calculator.